All right, so today's lesson, we're going to focus on looking at the emerging pathogens and their spread. So this is basically looking at all the pathogens and how we classify them as being either emerging or re-emerging based on how they are uh, ex- how they are presenting themselves in communities, and also talking about how they are spread, how they are managed and dealt with in a bigger scale. All right. Let's see the answer, but it's okay. Let's just go through this quick example. Rabies is a viral disease spread to people by infected animals. Basically, when an infected animal bites you, it passes on the pathogen that causes rabies, and a person bitten by the infected animal should be given an injection of that specific antibody. So they are being given the antibodies. That means that it is artificial. And since the antibodies are being supplied, they are not made by your own body. That is also passive. That's why the answer is artificially passive. All right. So I'm just going to get through a few bunch of things. Yeah, you can see that that's a lot because there's two topics in this. Right? So pathogens are basically based on two major factors. One is virulence and the other one is contagiousness. Even though you guys might use these words interchangeably, they actually have very separate meanings. Virulence is talking about how severe or deadly a disease is uh, that is going to be caused by a pathogen, whereas contagiousness is about how easily it can actually spread in a community. So one is talking about deadliness or how severe the disease is, or well, the other one is talking about how easily it can spread within a given population. By considering these two factors, we then get a overall sense of any disease's danger, right? How easily it can spread also influences how dangerous it can be, and how dangerous the disease that it causes is also important. For example, the way we look at COVID is that it spreads very easily, but in terms of its virulence, it's not as high as some other viruses that we've dealt with in the past. So that's still considered dangerous because it can spread to a lot of people. Whereas something like smallpox, that is a virus that is highly virulent because its disease is going to be severe and it can even lead to death. So those are how you should think of diseases. Consider these two things, virulence and contagiousness, and we'll get a better sense of a disease in terms of how dangerous it actually is. So when we think about diseases, there's two ways you can think of them, as either emerging or as re-emerging. So we have two examples here with monkeypox and with measles. So monkeypox is relatively new to you guys. It's a disease that was rare and commonly found localized within laboratory monkeys. But recently, there have been more outbreaks and cases that have been reported outside its normal regions, right? That's the keyword here. Recently reported outside its normal regions in multiple different locations. That means that this is an emerging disease. It is an infectious disease that is new to the population and is rapidly increasing in incidence. It's basically popping up in more places. It's becoming more, it's mentioned more, and it's also definitely popping up in places where it normally wasn't found. That's the key thing here, right? That's why it's considered as emerging. Whereas re-emerging is talking about a disease that has already basically had a foothold, but has went down in number or went down in incidence, and then caused a resurgence of cases later on due to some other factors, right? For example, measles. Measles was largely dealt with due to vaccination programs a while back. But nowadays, since people are getting more lax with their vaccinations, there has been a re-emergence or resurgence in cases. So that's why this would be considered as a re-emerging disease. And there are more examples of these emerging and re-emerging diseases where we can actually classify all the diseases caused by pathogens as by either being emerging or re-emerging in different scenarios. So what can cause these pathogens pop up and actually emerge or re-emerge, there is a bunch of different causes that can lead to. For one thing is the evolution of causative agent, right? This is an example of when it can cause re-emergence, where the pathogen itself, the causative agent, has gone through evolution. So uh, whatever changes it has acquired is allowing it to become more dangerous or more virulent or possibly even more contagious. That means that it either acquired resistance to pre-existing treatments or it has suddenly become much more contagious, being able to spread faster. And this happens very often with viruses because they mutate and become either more virulent or more contagious through time. Another one is globalization and travel. The fact that there are people traveling from different parts of the world all around at the same time, that means that any pathogen has the potential to travel across borders without any trouble. So being isolated in this globalized world is not very easy anymore, where pathogens can just travel all around. And that's what you could see happening with COVID at the start, right? It started at one point in Wuhan, but due to the many factors, it managed to slip through the borders and just spread to almost all countries in the world very quickly because of globalization and travel. Next is the increased exposure of humans and animals. So there are some diseases out there that we can never get, that animals can get, and that also works with uh, us and sorry, basically animals and us have a species gap, right? Diseases can't jump that species gap that easily, but there is a potential when there is increased exposure between animals and humans. If we're just spending too much time together, there is a higher chance of zoonotic diseases being able to jump that species gap and start infecting humans, right? We see this with a lot of diseases, even COVID, prime example of that, right? First, COVID was only found within the bat species, but somehow that strain of COVID, that strain of the virus, was able to jump the species gap and actually start infecting humans and cause the problem it did so far. It's the same with, if I remember correctly, HIV as well. At first, it was a zoonotic disease, and then it jumped the species gap and managed to start infecting humans as well. And moving on from that is the increasing human population. So another factor that causes the emergence and re-emergence of pathogens is the fact that there's so many people out there. That means sometimes there can be situations where there's a lot of people gathered within a small amount of space, meaning a high population density. Think of a city like Hong Kong, or the slums in India. These are places where a lot of people are converging together, and due to poor sanitation, it can even have increased pathogen spread and allow for the emergence of different pathogens as well, right? You're more likely to spread a disease to someone else when you are stuck in a very small space together, right? Think of uh, stuck in a small house with 50 people, you're going to spread a disease to all of them if anyone gets sick. That's what's happening here. If there's an increased population in a certain place, the chances of a disease or a pathogen emerging in that sorry, in that dense population density is higher as well. Next is changing technologies. This is not something you see very often, but it can be the case where the development of a certain technology actually allows for the re-emergence of a disease, specifically Legionnaire's disease, and they actually manage to re-emerge due to the action of air conditioners, right? Air conditioners give a suitable environment for these Legionnaire's disease to re-emerge, and thus we can also see why that causes the re-emergence of a pathogen. Next is insufficient vaccination of a population. So in that, essentially think of when an entire population was vaccinated, but over many generations, no one's keeping up with the vaccinations. So herd immunity lowers and lowers until it has lowered below the threshold, meaning that people can actually start to get infected more easily due to the fact that there are more and more gaps in the herd immunity that has emerged. Any questions about any of these factors, right? All of these are potentially leading to the re-emergence or emergence of many pathogens. So you guys can always use this as examples in your questions. So this is what I mean by when I say that they are going to be primarily within the populations of animals, either as wildlife or as livestock. And then over time, due to increased exposure to humans, they've actually jumped the species gap and are now able to infect humans as well. And this can potentially happen the more time we spend with animals and livestock in situations we're not supposed to. So the potential of a pathogen to be spread all over the world. We've already seen that in the past before COVID even happened in 2002 with SARS-CoV-2, where even though it started in a where did it start again? Yeah, occurred in China in November 2002. The virus managed to spread all over the world within a short time frame. By April 2003, you can see that it spread through most of the planet because of the fact that we live in a globalized society, right? Travel is so easy, crossing borders is so easy, and we can carry the pathogen within ourselves, so it gets a free ride to wherever it wants to go. In fact, if we look at the spread of COVID, you'll see something similar as well. The first case, Wuhan, right? And you can see how it changes over time. Anyone has ever played Plague Inc., that game, you definitely know what it's like for a pathogen to spread. It's literally so easy right now because of the fact that even though we have a lot of strict measures, especially the Australian Border Force, they do whatever they can to prevent unapproved stuff from being imported in. You can't protect against a pathogen that is literally on your body or inside you, right? They can't detect it, so it can be spreading as easily as the air that we breathe, and you wouldn't know about it until it's too late. And this can happen very easily. And that's why even right now, if you guys haven't heard about the whole monkeypox thing, it is spreading to different countries very easily, and people are getting very worried, and it's triggering some old COVID trauma. Right? So examples of emerging and re-emerging diseases, you guys have probably heard of most of these: Ebola, measles, cholera, malaria, corona, 2000 pandemic influenza, and AIDS. A bunch of these you guys have heard of. Some of these have been around for a while, and they keep emerging, re-emerging, and then going down. That's why they are considered as being re-emerging diseases, and they are caused by different causative agents, right? Causative agent is the same as the pathogen, where they are the ones leading to the disease itself. There is a very big difference between the pathogen and the disease. Disease is what the pathogen causes, and the pathogen is the causative agent, right? And let me show you guys what are the contributing factors for them having emerged or having re-emerged. So with your Ebola, it is thought to have jumped the species gap, where through zoonosis, it was able to jump the gap between the species and start infecting humans. With measles, it was due to the fact that vaccination programs were not followed through, or there was a reduction in the coverage, leading to the re-emergence of the virus. And another example is malaria, where the pathogen was able to evolve resistance to the drug. So that means that it was able to actually combat against treatment and actually grow in spite of it. That means that it re-emerged as a result. And COVID and a bunch of those diseases are considered as emerging because they were very small at one point, and then suddenly it started appearing in different regions. It started increasing in incidence, and that's why we consider that as being emerging, right? So depending on the level of emergence or re-emergence, we can actually classify them in three different categories. One is epidemic, the second one is pandemic, and the third one is endemic, right? Three of these things are basically uh, describing the level of spread of the specific disease within a certain population. So let's talk about what these three mean. So you guys probably know what a pandemic is, having a very recent occurrence of one. A pandemic is essentially when a sudden increase in cases in several countries around the world is occurring. Basically, it's popping up in a bunch of different countries at the same time and is not being able to be controlled. That is why we consider that as being a pandemic. When it comes to endemic, that is right. Epidemic, that is basically it spreading through a specific population in a specific country. So let's say Australia suddenly had a very high rise number in monkeypox cases. Sorry, let's try a different disease. A high number of this one right here. This is epidemic to Australia with more disease. So let's say yes, suddenly but it's only happening in Australia, it's staying within our population. That is when we call that a epidemic. Basically, it is spreading through a large population, but it has not crossed the country lines to go spread into different regions, right? And then when we're talking about endemic, this is basically where a disease has uh, reduced in numbers, but it's still present within a population with relatively low spread. An example of that within our Australian population is rhinovirus, or you guys know it as the virus causing the common flu, right? No matter what we do, right? No matter how we are, rhinovirus will still persist in Australia, even though there's a low level of spread. That is why it's considered as being an endemic disease, because it is going to constantly be present, but at a very low level of spread. So we can't really get rid of it, but we can control how much it spreads. That is when we refer to it as being endemic. So an example of that is COVID right now, right? Most people have gone to the phase where we consider COVID as just being an endemic disease, because even though it is still present, it's still going to be around, it has been reduced to a level where it is spreading very with a low relative amount of spread. All right. So when we let's take a step back and think about when these pathogens were reintroduced to different populations, specifically when the Europeans arrived in Australia all those years ago. So why is this a problem? When different populations interact, they are potentially spreading different pathogens to each other, right? And more often than not, the more developed society or community that is what's the word? Crossing paths with a population that has not developed so much will always affect the lower development, because that means that they haven't gotten the immunity to a lot of pathogens, right? So let me try to point this out. Europeans arriving in Australia in the 18th century brought with them a number of diseases that quickly spread through the population, because the population that they were looking at in Australia were not immune to a lot of these diseases and pathogens that the Europeans brought in. So, for example, smallpox, syphilis, tuberculosis, influenza, measles. When they brought in these random diseases into Australia, they spread like wildfire because of the factor that they had no immunity to these diseases. That means that it can spread without any control. So that actually led to widespread disease and death that you can actually see in the trend here, right? So if we look at this trend right here, you can see when this is the population of Australia, the purple line. This is the number of colonists in Australia, and you can see the anyway. So this is assumed to be the number of Aboriginal people in Australia as well at that time, and you can see that at one point there is a inverse happening where the number of colonists suddenly increase and the number of Aboriginals decrease. This is showing the trend where colonists are starting to emerge in Australia and the diseases are being spread, causing mass dips in the population, the indigenous population. Yeah. Is this North Sentinelese people? 100%. This is exactly the reason. I actually was going to point that out. Even now, in the current age where we live in, we have to be very careful about exposing communities that are very reserved or basically haven't interacted with the developing world out large, because we have basically developed our immunity over many, many centuries of innovation and technological improvement. And we've actually developed our immunity to a lot of different diseases that we don't even think about, right? We've gotten immunity for smallpox, for example, that we got it very early on, but these communities never had that chance. That means that if by any chance the pathogen is within us or we are carrying it and they are exposed, they will have to go through the whole case of getting infected and experiencing all that death, right? So when we're thinking about why these factors are thinking, why is it that populations are exposed and so affected by these emergence of diseases? There are a lot of factors affecting immunity within an indigenous population. One thing, obviously, a lack in immunity is for one of them. The second is a lack of knowledge and experiences with European settlers. And third, and most importantly, is the disruption caused by colonization. Right? These three factors compounded together to basically hit Aboriginal people very hard when the European settlers came in. And that also meant that they experienced a high amount of death early on due to this exposure. So the first thing is the lack of immunity in the indigenous population. If you were never exposed to the disease, you can never develop immunity to it. So obviously, when a population coming from Europe has experienced very different selection pressures, very different kinds of pathogens, they have developed immunity to very different things. They come in, they bring in the pathogens that they had, they're gonna infect all the people in Australia, right? So, like we've talked about, smallpox and all those things, it basically hit Australia, the Aboriginal people in Australia, without any warning, due to the fact that none of them had natural active immunity. Only after being infected can some of them even develop that. And that's why there was a lot of death early on. Right? Any questions? Moving on. Next is the lack of knowledge and experiences with European diseases, right? So essentially, indigenous people have accrued a lot of scientific knowledge and discoveries within their community and within their environment, right? However, when Europeans arrived, they brought in new diseases, right? Diseases that Australians were never exposed to and never had any knowledge about as well. So they had no knowledge of how to treat the symptoms, no knowledge of what to do in certain cases. This meant that they are going to be worse off in that situation. So their ability to practice indigenous medicine was also prevented back then by the Europeans. So that meant that indigenous people were left without any form of medical treatment to help them when they were infected as well. And lastly is the disruption caused by colonization. So essentially, before colonization, populations lived well adapted to the local environment and they basically survived on their own. But when European populations invaded and they colonized the indigenous people, a lot of disruption was caused where food, water, access to medicine, all these normal things that Aboriginal people could do for themselves were basically prevented, halted, or basically controlled. This meant that a lot of Aboriginal people were in a state of suffering, and that meant that they can't get the things that they need. In fact, if we look at it in terms of statistics, it's found that in Victoria, throughout the first 50 years of contact with European settlers, over 60% of the indigenous population has succumbed to a series of epidemics. And this continued all the way into the 20th century with negative impacts of the European arrival still being felt until today. So essentially, the effects of colonization are felt all the way through until today. So now that we've looked at basically the pathogens and how we classify them in terms of their danger as either being virulent or contagious, how easily they can, how dangerous is the disease that they cause, how severe it is, and with contagiousness, how easily it can spread. Basically, we classify them as being emerging or re-emerging. Now let's look at how we look at the spread of these pathogens, right? So before we go through that, let's just do a quick recap what we were talking about. So in this case study here, I want you guys to consider whether it's an emerging disease or re-emerging disease. So have a read here and you guys tell me whether it's emerging or re-emerging. All right, can I get Ma'am, would you like to read that? The top part. Hmm? Yeah, the top part.
Smallpox is an infectious disease caused by
Sorry.
Smallpox is an infectious disease caused by a variola virus. This can spread through airborne respiratory droplets, saliva, skin-to-skin contact, and blood contact. Smallpox had a mortality rate of 30% with no treatment or cure. In the 1980s, WHO has confirmed that smallpox was eradicated from the vaccine. However, there are samples of smallpox in certain laboratories. If a scientist was infected with the smallpox virus, identify and explain the type of disease.
And essentially, yeah, this disease was very dangerous, and then we vaccinated the populations, and it was eradicated. But the situation is that now a scientist has suddenly reinfected themselves because they don't know how to work with pathogens. So where would you classify it? Is it good? Is Gertrude's response right, or is Katie's response right? I don't really know why that whole Gertrude and Katie thing is there. But who thinks it's Gertrude? Who thinks it's Haiti? Yes, it is Haiti. It's obviously a re-emerging disease. So as long as you know the difference, emerging, re-emerging, it should be straightforward for you guys. So now let's look at why we need to control the spread. Before we can control the spread, we basically need to know what we're dealing with, right? Why can it be important to actually identify the invading pathogen? Because that has to do with knowing how to control the spread. We can't control the spread of a pathogen unless we know what pathogen it is and how it's actually spread. So we need to first find out what is the pathogen. In fact, that was the problem with COVID at the start, right? When COVID emerged, there was so much uncertainty about how easily it can spread. People were unsure whether wearing a mask was effective or not, whether it's so hard to spread that we can be in the room with another person who's infected and not worry, or whether it's so dangerous that just a person being in the room before we come into it can potentially lead us to being infected as well. So there was a lot of uncertainty on how a disease spreads, and that's because we were not aware of the disease, of the pathogen itself, or we are not fully informed about the pathogen itself. So that's why it's important to identify the pathogen and learn everything we can about it in terms of its physical, phenotypic, immunological, and molecular characteristics. So by finding these four, we can much easily identify the pathogen and its different features. So why is it also important to not assume we know the pathogen? Because something that can happen is that it can be very similar to a different pathogen, but due to mutation, it might have changed it slightly in a way that it either increases its virulence or its contagiousness, right? There are versions of COVID that are out there that are not as virulent or even more virulent than the one that we've had to deal with. And this can be the case due to mutations. So we need to actually take every case of a pathogen as if we're looking at it brand new and treat it without bias at all. So the four ways that we can basically identify pathogens using is the first one where we basically assess the visual features, the physical features, and visualize what kind of characteristics it has. Just purely on a physical level, we look at it, we see what we can identify. So when we did it the other day with the pictures, we could tell that with bacteria, there are three distinct shades, right? We have your cocci, we have your bacilli, and your spirochetes. Okay, and these are looking very different, and this is specifically for bacteria. For different pathogens, there are different features we're looking at. For example, with the virus, we're looking for capsules, right? Whether they're encapsulated in a capsule, that is a sign that it could be a virus. And with different pathogens, we're looking for different features. So this is the first step. Moving from there is the phenotypic assessment. Yeah. Phenotypic assessment, meaning that the features that it exhibits. The first one is how selective agar plating. That is basically plating these different this pathogen on a bunch of different plates that are selecting for different pathogens. Basically, to know which pathogen we're dealing with, we have to plate that pathogen on plates that are very specifically only going to allow that pathogen to grow. For example, let's say we have a sample of Legionella this pathogen right here. This pathogen will only ever grow grow on a buffered charcoal yeast extract plate. So if we don't know that we don't know what this pathogen is, we just have that sample getting people sick. We plate it on a bunch of different plates. None of them allow for this pathogen to grow. And then suddenly when we use the buffered charcoal yeast extract, this pathogen suddenly is able to grow. That shows us that it's definitely got to be this pathogen because this pathogen selects for that plate. Basically using the plate to identify the pathogen through selective agar plating, right? Let's say we have 50 plates, each of them is selecting for a specific pathogen. We will plate on all of them until one of them shows a growth. And when there is growth on that plate, we will then also trace it back to what pathogen can actually grow on that plate, and as a result, we'll know what pathogen we're actually dealing with. Okay, anyone confused by selective agar plating? All right. Moving on from that is our biochemical test panels, right? And this is specific for bacteria only, where we are going to be asking dichotomous questions that allow us to finally determine the samples genus and species, right? So this is the one that you guys did the other day at your excursion, where you basically start off with the first question, gram staining, right? Whether it's gram negative or gram positive, we determine that by staining the bacteria, seeing how much purple it retains. If it's a dark purple, that's gram positive. If it's a light purple, it's gram negative, if I remember correctly. And we'll start off from there and then do more and more tests at every turn. We will better understand what possible bacteria we're dealing with. So for example, if we know it's gram negative, we'll know that we need to do a citrate transport and hydrolysis test. And then if it's negative, we know that is a E. coli. If it's positive, there's more options, and we'll keep doing tests until we find out which bacteria we're dealing with. Another example here, right? So we start off by looking at the physical feature. We know which type of bacteria it is. After that, we do the different tests, and we'll finally be able to narrow it down to one specific bacteria. Any questions about this one? All right, moving on is our immunological identification step, which is basically using a serology technique where we use the antibodies or antigens in a person's serum. So to know, basically it's done using that ELISA test that you guys did as well. And it can be direct, indirect, sandwich, or competitive methods. We're going to look at the sandwich method in a bit. But this is basically using the antibodies or antigens in a person's serum to determine what is the pathogen that they were infected with. And lastly, it's the molecular techniques that we can use. The obviously whole genome sequencing that can provide a lot of information and possibly even allow us to identify which family of pathogens it belongs to. Then another one is hybridization-based detection. If we have the genetic code of a bunch of different pathogens, we can then basically use label segments of genetic materials of different pathogens and expose the sample that we have with those label segments and see which one will bind to the complementary sequence on the sample pathogen. And when we have a response, that's when we know which pathogen we're dealing with. So it's the same as the selective agar plating. We're just testing it with a bunch of different known samples such that when we get a complementary match, we know which one we're actually dealing with, right? In this example, we're using a plate that is selective, but here we're using the DNA segment, or sorry, genetic material segments, and seeing which one is complementary to the samples that we have, and then we then know which pathogen we're actually dealing with. Okay, everyone clear on this? The four different ways? Moving on. All right. So let's talk about the ELISA test a bit more. Where how it works is first we have a plate that has the wells coated with the antibody. All right. So first we have a well coated with an affinity purified antigen specific antibodies. Basically, antibodies that are going to let these sample antigens bind to them. We will wash the plate with that. And once the antigens have been bound, that's when we expose them to a bunch of different antibodies. And then we will basically see when the antibody actually binds to the antigens. And once we do that, we basically do the step with another kind of antigen and see whether it releases the detection method. Obviously, since there are so many different types of ELISA tests, whether they could be direct, they could be indirect, they could be sandwich or competitive, there are many different versions of this test. Essentially, it works by introducing the antigen if the organism has antibodies for it from vaccine or exposure, and it will coagulate and become visible. Right? First, we introduce the antigen, and then we will try to wash it with a bunch of antibodies. And if it binds to the antigen, that means that it will become visible, and we know whether that pathogen is present. Specifically in this example, let's just go through this very quickly. So first, antibodies specific to a certain pathogen are linked, basically plated with the plate, where we have multiple plates will be tested with the pathogenic antigen. Then the serum sample to be tested is applied to the plate, where the pathogen antigens present will start attaching to the antibodies. Third is the second detection antibody linked to the color changing enzyme is added to the plate that binds to the antigen again. So essentially, we have the antibody which is plated with the agar plate, and then the pathogenic antigen is exposed to a bunch of these different plates, and one of them will actually cause the antigen to bind to the antibody. And when we do the second detection antibody, that's when the antigen allows for the antibody to also bind to it. And this is why this is the important one, because this has the detection enzyme linked detection. Right. The enzyme linked detection antibody, meaning that it will actually present itself, meaning it actually identifies when the sample has actually been triggered. Moving on is the modes of disease transmission, right? These are basically talking about how a disease can be transmitted. Let's just show the examples first. So first is your fecal oral transmission, and this is as disgusting as it sounds. Essentially, what this one talks about is when fecal matter, or let's say this poop, people they get exposed to poop through improper hygiene or whichever way, and then they make contact with different objects, and through that diseases can spread. Specifically, stuff like E. coli, which you can find on poop, can be spread through the fecal oral transmission, where people with fecal matter on their hands or different parts of their body transmit it to different people when they grab those things, right? For example, let's say person A didn't wash their hands after using the toilet, and then they go cook a meal for their family. They are basically then exposing their entire family to all that fecal pathogens. The next one is your classic airborne transmission. This is basically when we are breathing, the air that we release is also exposed to all the pathogens in our body, and any pathogen that is capable of being transmitted through the air will basically basically just by breathing it gets exposed. Next is your droplet transmission. This is basically when someone coughs, sneezes, or coughs or sneeze. Those are the most common ones. That can lead to the pathogen being spread from one person to the next. And this is the one that you guys probably have a lot of experience with. Next is direct physical contact. That is also another way that pathogens can be spread. And lastly is indirect physical contact. So difference between direct and indirect is where direct, you are basically making a contact with the person with the pathogen, whereas indirect is when you're making contact with something the person with the pathogen has touched. For example, if person A who is infected with the pathogen makes contact with the handle of the door and then goes about their day, whenever you touch that handle, that is indirect physical contact, because the pathogen is probably still there on the door handle and can easily be transmitted back to us if we don't practice proper hygiene. So we have a bunch of different diseases on each of them, and each of them has different features. For example, with airborne disease, the pathogen is small particles traditionally smaller than 5 micrometers, and they stay in the air for prolonged periods of time. And this can be due to the fact of a person sneezing, coughing, even exhaling, right? They have these particles that can just persist in the air. And think of it like this. Think about the air that we breathe, right? The oxygen that we breathe out or the air that we breathe out. It carries particles from inside our body and they just hang in the air, right? It takes a while for them to actually sink to the bottom and get to the floor. So they will just float around. And if another person just walks through them, it will go into your nose, it will go into your body. Basically, that's how you can get infected with your airborne infection. And that was the case with COVID-19, where people who were infected were basically breathing out that disease. And that's why it was so easy to spread as well, where if a person infected is in a room, that room is filled with the pathogen. Anyone who walks in has the potential of catching the pathogen as well. Next is droplet transmission, where respiratory droplets can remain suspended in the air. So instead of just being small particles, this one is more about small droplets, right? Physical droplets that are going to persist or suspend in the air much longer before they fall to the ground. And if they touch or come in contact with those droplets in their eyes, mouth, or any other openings, they can get infected as well. So with airborne transmission, most of the time, the first line of defense protects us from that, right? We are exposed to a lot of pathogens in the air, but we don't necessarily get infected because our first line of defense is putting up a physical barrier between outside and inside. But if we have our mouth open and someone sneezes into it, there is no first line of defense anymore. It literally goes into your body. So obviously you're going to get that pathogen. All right. Next is your direct. About everything from kissing all the way to sexual contact, sexual transmission. They are all they all fall under direct physical contact because they are all forms of basically physical contact, right? This can cause the spread of everything from HIV all the way to athlete's foot as well. So it's a very wide range of transmissions that can happen when it comes to direct physical contact. Some diseases, they require not just normal physical contact, they need what's the word I'm looking for? Sharing of bodily fluids kind of physical contact. That happens basically during sexual intercourse. And another example that can also spread disease is also kissing, but not all diseases that spread through kissing, sorry, not all diseases that spread through sexual contact can spread through kissing, right? For example, HIV, which spreads through bodily contact, is very specifically needing specific type of bodily fluids to go into different parts of the body to actually infect the person. So kissing is one way that you won't get HIV because that's not the bodily fluid that is going to be that's going to be able to carry the pathogen inside. So yeah, why am I so uncomfortable talking? Moving on, indirect physical contact, right? This is basically when we are getting exposed to a pathogen through means of the first person using or touching something, going away, and then us making contact with that, right? So for example, if someone was sitting on this chair, blowing their nose, they are already transmitting that pathogen onto the tissue, right? And then imagine I come in here, I don't notice that they did that. I take that tissue and I wipe my face with it. Yeah, I'm basically getting exposed, and that is indirect physical contact. Basically, no direct contact between the host and myself, but I'm still getting the disease. That is why it's considered as indirect physical contact. So it spreads through something we know who are called as fomites. These are basically things that can carry the pathogen whilst it is coming out of the host, right? So it could be food, water, tissues, needles, whatever it is, right? It's carrying the pathogen from the host, and it will act as a vector, but it'll act to infect the secondary person when they come into contact. This can also be happening through vectors as well, where think of a mosquito. The mosquito comes and lands on the host. It sucks the blood, but it's also getting exposed to the pathogen, right? It's carrying that pathogen and then flying to another person, landing on them, injecting their blood, and also transmitting the pathogen while it's at it. That is also an example of indirect physical contact, because it's still coming from the host and there's no contact between the host and us, but we still get that pathogen from the host. That is indirect physical contact. And lastly, fecal oral contamination. Yeah, this one really weird and disgusting, but it does happen more often than you think, where people don't practice great hygiene after using the toilet, and they are still exposed to pathogens that are known to be found in poop, and that pathogens later spread on when that person who has not practiced good hygiene has basically come in contact with other stuff. So even though it is considered fecal oral transmission, you can see where it overlaps with other forms of transmission as well. So even though the pathogens excreted are being consumed by the person indirectly via contamination, they can then spread it through the other means, right? Airborne or droplet, but it still falls under the fecal oral transmission because that's where it started, right? So there are a lot of ways that a disease can spread, and it's very, very important to take this into account when we are trying to deal with a pathogen, right? There's no point protecting ourselves against airborne pathogen when it's only spread through physical contact, right? We don't, for example, something like monkeypox. Monkeypox is prominently spread through direct skin to skin physical contact. That's the most common way it's spread. So we don't have to suddenly start monitoring the air for these pathogens. We just have to make sure we monitor everyone's physical nature and see whether they have any rashes that are tied to monkeypox, and we can try to avoid the transmission. So that's why identifying the pathogen is always the first step. Second step is learning how it spreads. Third is then dealing with that transmission to prevent an outbreak. So that's what we failed to do with COVID. Right? And obviously the last, this is the this is why most diseases end up spreading, even though sorry, not most, a lot are actually dealt with behind doors, but even though we can deal with a lot of them, some can still slip through the cracks and cause pandemics and endemics, epidemics, and become endemic because diseases are tough, and some of these steps require us as humans to work together and actually be very serious about it, which hasn't always been the case, right? For example, prevention, right? Taking steps to prevent the disease. Something as simple as getting vaccinated could help prevent the disease. But as I said, not everyone is going to do that because of different beliefs, different ideas. That allows the disease to still stay in the population. Prime example, measles, right? Measles was at one point very much dealt with through vaccination, but in the current age that we live in, it has actually re-emerged in different communities because people are no longer doing the vaccination for measles. Thus, it is actually being able to re-emerge. So prevention is super important, and it can actually end up saving lives before we even need to deal with the issue. Next is ongoing surveillance of disease indicators. Basically, looking out for certain symptoms or medication sales at pharmacies that show an increased prevalence of a certain symptom or illness in certain communities. So, right, let's say a small community in some developing country suddenly has a lot of a specific symptom, right? They are suddenly getting a lot of rashes with weird bumps in this small community. That is gonna trigger alarms, right? Because why is there such a specific symptom occurring in such a small community, and it's very prevalent as well? That could show signs of a emerging pathogen that is actually starting to spread within that community. So those are signs or indicators that can allow us to actually start taking steps early on, right? Next is quarantine and isolation. Obviously, this method is something everyone is familiar with. For example, myself, when I went back home during the COVID pandemic, I had to quarantine at a hotel for 14 days. Even though back then we didn't know, we were still learning a lot about this COVID. Now we know that just around 5 days of isolation should be good for you to go back into society. But back then they were still unsure. They still needed more data. So they just gave a blanket quarantine period of 14 days for everyone, regardless, because it is a very good step, right, in controlling disease transmission. Quarantine and isolation is still practiced as one of the most effective steps in controlling a disease, because we can basically isolate the transmission from going uncontrollable. Next, obviously, identification of the pathogen. Yeah, the rest as well. Yeah, that was pretty much it. The next parts are talking about what we use to deal with the diseases, disinfectants, antibiotics, and antivirals. And yeah.